Hi there, welcome back to Petrophysics Rocks. This presentation goes along with the first one. This is the applications presentation. This is the examples of my flow conditioned permeability modeling presentation. Hopefully you've watched the first one. And that explains the methodology and how and some of the maths behind how I get to the flow capacity of the rocks. Obviously in the reservoir we're interested in how quickly we can get the oil out and at what rate it flows out to determine whether we have an economic development on our hands. And now I'd like to sort of go through and share a couple of examples with you in the so-called real world. These presentations originally on my website were two, but I'm hoping to be able to combine them together. So if you've watched the first one and liked and subscribed and maybe commented down below on some remarks, that would be good. And what I'd like to do now is sort of like go through these two presentations. The first presentation is around about upscaling and reservoir cutoffs. So upscaling is the process by which we take all of my well-log data and upscale it into a computer model. So when we make wireline log measurements, we make them at 6 inches, every 6 inches down the hole. And we make gigabytes of measurements, if you like, downhole. So we've got a lot of measurements, at least 20 or 30 measurements every 6 inches down the hole. And in a reservoir, you could imagine that's 1,000 foot thick. If you're lucky, then that's obviously quite a bit of data to cope with. So what we do often is we take that data and then we upscale it to the reservoir scale to layers. So we might model, a reservoir model might have one value for every 1 or 2 meters thick sort of thing. So we take all of that fine scale data and upscale it into the reservoir model. Now, what we need to do is we need to make sure that we're not losing any information by making those simplifying assumptions. And so I found that flow conditioned permeability modeling is a good way to visualize and get a feel for how much flow capacity we're potentially losing in every upscaling step. Every time we take an average of a bunch of layers, then do we lose flow capacity as we go through it? And it gives us a little bit of a stronger argument when we come to assessing how our reservoir models perform, if we understand the modeling, how much of the information has the modeling process itself taken out, and how much is real geology sort of stuff. And the second part of the first presentation is the net sand cutoff debate. In my line of work, in our industry, we often use lots of rules of thumb. There's one called a 1 millidarcy cutoff, which means that if you've got an oil reservoir, it needs to have at least 1 millidarcy permeability to flow oil. And you might use a 0.1 millidarcy cutoff for gas. So gas will flow at permeabilities down to 0.1 millidarcy. And those are kind of common rules of thumb that we use. So this presentation at least attempts, probably muddies the water a little bit, but it tries to get to what does that actually mean? What does 1 millidarcy foot cutoff mean? Or what does 0.1 millidarcy cutoff mean in terms of the flow of fluids in our reservoirs? So hopefully at least gives you some food for thought, for discussion around about that. And then the final presentation, the final example, is some flow rate prediction work that I did for a field, a low productivity field in the North Sea where we didn't have any real data. So I made some up, and then we came up with a range of possible outcomes. So we had to decide whether to invest in this particular job or not with no data. So using these kind of techniques, I was able to make something up. Hopefully it was reasonable. And actually, when the work was done, a year after I left the company, the results that I predicted were pretty accurate, actually. None more surprised than myself, I have to say. I might do a separate presentation on that as well, because I did present that later to an SPWLA topical fall conference in Asheville, North Carolina, got me over there to present this results, and so I might do a separate presentation on a bit more detail on that result. But because it all worked out fine, I'm happy to share it. Anyway, as I say, like and subscribe, and if you'd like to comment down below, even if you just put in where you're watching from, that's very interesting to hear, and it also helps the YouTube algorithm. Any sort of interaction is appreciated. Okay, so we'll go straight on with the first applications one, and then it'll sail right into the second one, and hopefully I'll see you back here next weekish for a further video. Alrighty, cheers then. Thanks a lot for your attention, and I hope you enjoy these presentations. This is the first applications presentation of the flow condition permeability modeling series. I'm hoping to illustrate some issues around upscaling and also touch on concerns about net cutoff definition. What I'm hoping to do is be able to show you that how I can use this flow profiling approach that we've developed to evaluate the validity of the upscaling process that we go through often from core to simulator scale. And indeed, as I've already shown you, I think that core regression techniques are already a form of upscaling, and so if we can use this process to get a better degree of confidence that we're not missing out on anything as we go through the various upscaling stages, then hopefully this will be useful in our evaluation. I'll show you some field examples of this, and then finally the last part of the presentation will touch on some cutoff investigation and what's the relevance of this much quoted, much talked about 1 millidarcy cutoff. What does it mean in the real world? I hope to illustrate some issues around this and give you a better, and again, a gut feel of what's going on in the physical world when we talk about things like a 1 millidarcy cutoff. But first of all, let's start off with the upscaling issues. So here we are. Here's the core prediction. You should be familiar with this spreadsheet by now, really. We've got some assumptions about the in-situ reservoir conditions and also some assumptions about the fluids and the wellbore geometries, and therefore we use that to calculate an inflow profile. Now this particular plot here, I've got an extra track in here where I'm showing the core porosity, the symbols overlaid with the log porosity. In addition to the core permeability in this track, overlaid with the predicted permeability. Okay, so in this particular case, you should be familiar. You may recall that it's quite a low permeability reservoir, only anticipating about 400 barrels a day of flow from this particular reservoir, and here we have the predicted fit to this core data, which quite closely matches the bin arithmetic averages here, and this is the air permeability fit, and then we subsequently correct that to the in-situ brine permeability here shown in the green, and then this green curve is used in the calculation of this inflow profile. Now I happen to know about this particular core set that in fact there are two fascies here. We've got a cloud of data around here, that's one fascies, and then this lower cloud here is another fascies, and those relates to these two lower sands here. So here we are, we've got 154 millidarcy feet from this core data, and this is the predicted permeability profile through that core data, and then as I say we brine correct it down to the green curve which calculates this inflow profile. Now what happens when we go to the log data scale? Here we are. Now instead of using the core permeability, we're predicting a permeability from the log porosity. So
these become straight lines now, as what you typically expect to work their way into our reservoir models, straight line pore-perm relationships. If I just toggle back between the two, you can see what's going on a little bit better here. So these two fascies become these two pore-perm trends that we're using, these straight lines, and we therefore calculate, instead of the actual core permeability, this is a predicted permeability from this core data. And the eagle-eyers amongst you will notice that, in fact, the inflow profile is a little bit higher here in the log data in this particular example than it is with the core data, and that's really because, in fact, you can see that I'm slightly over predicting my log porosity here compared to the core porosity over this particular interval, and therefore I calculate a slightly higher permeability. If I toggle backwards and forwards between those two, you see the higher porosity here gives me a higher predicted permeability. So in this particular case, it makes it a little bit tricky to evaluate the upscaling process, because normally it doesn't go this way, but in this particular case you can see that I've gone from a core data set, and I've actually increased the permeability in this particular example, and now I'm producing, instead of, I've gone from 424 barrels a day, I've gone up to 870 barrels a day. So there's clearly something else going on in addition to any upscaling concerns. But you can see I've doubled the millidarcy thickness as well, the permeability thickness in millidarcy feet. I've gone from 154 millidarcy feet to 300 millidarcy feet. But anyway, in any event, this is the log prediction. I've got my two straight lines here, and this was what would typically go into a fine scale geological model, and then be used as part of the log data prediction set to build a permeability model. So if we go to that Petrel model, or any geological scale model where we're upscaling slightly from the half-foot depth increment to, say, 1 or 2 foot layers, here you can see this squared off log here is my simulated porosity in the model, hence it's square. And using the same sort of pore-perm techniques, you can see the difference in permeability thickness and inflow profile as we go from log scale to Petrel scale. And this is what I mean by it's quite useful to be able to check the efficacy, if you like, of our upscaling process. So we've gone from 316 millidarcy feet and a flow rate of 870 barrels of oil a day. We've upscaled to the Petrel scale, and we've lost some permeability. We've gone from 300 millidarcy feet down to 220 millidarcy feet, and we've lost a couple of hundred barrels of flow rate as well under these assumed flowing conditions. So this is what I mean when we can use this type of technique to say, okay, is that a particular problem for us? Is that what we expected? Is it particularly biased? So we can check from log data to core data in a very visual way exactly where the rubber hits the road, if you like, and how much permeability we're losing, and also as a byproduct out of that the flow rate that we're using. And we can use this kind of thing to check our models to see that we're not introducing a systematic bias. So we go from 300 millidarcy feet down to 220 millidarcy feet. Is that significant for you in your reservoir? That's the key thing. So if we look at another field example here now, I've got 3 wells from a particular field. This example here is a log data set. Again, you see the straight lines, so this is log porosity transformed to straight line permeability. And in this particular example, I've got 5,951 millidarcy feet, and that produces 1,584 barrels of oil a day. In fact, that's the flow rate from this upper interval here, this perforated interval here, and that compares obviously down here over the whole interval. I've got, what's that, about 15,000 millidarcy feet, and you can see that I've perforated the top third of it, and so my millidarcy thickness, my permeability thickness under perforations is just under 6,000 millidarcy feet, producing 1,500 barrels of oil a day at the log data scale. Now if I go and do the same thing as I did before, go up to Petrel scale, so we've gone to slightly thicker layers, 2 or 3 foot layers in this particular case, and you can see that I've lost permeability thickness. So I've gone from 5,950 feet down to 5,620 feet. Not that much actually, in fact, is it really? So I've gone from 1,500 barrels a day, slightly over, to 1,500 barrels a day, slightly under. So in essence, I guess I would conclude from this that my Petrel upscaling is a pretty faithful match to my what the Petrophysicist intended, and I haven't lost too much permeability between log and Petrel. And in this particular example, I've an eclipse scale, a much thicker scale reservoir model. Typically in reservoir simulation models we can't handle the high resolution geological models, so we have to make thicker layers, and again that's part of the upscaling process. And in this particular example you can see we've gone to much thicker layers by, from memory, I think they're 5 to 8 feet thick layers, and you can see that the permeability thickness that we're maintaining up into the eclipse world is 5,300 millidarcy feet. So still, it's not too much of a loss. We have lost some, but not too much, and we're still at 1,400 barrels of oil a day. So I've got some other examples, the same thing. Here we are, 13,500 millidarcy feet under perforation in this particular example at half-foot log interval at depth increment, and if I upscale that to Petrel scale, 2 or 3 foot layers as I recall, we drop down again, we lose permeability thickness down to 12,200 millidarcy feet, and we lose a bit of flow rate as well. Let's go back, 13,500 millidarcy feet, just over 12,000 millidarcy feet, so 3,600 barrels a day down to 3,256 barrels a day. Not too much really, not too much of concern. If we go to the eclipse, we do lose a fair bit there at this particular scale. So we lose 2,000 millidarcy feet, so we come down from 12,200 millidarcy feet to 10,200 millidarcy feet, and of course the consequent inflow profile drops as well. So this is probably of more concern. We have to be a little bit wary when we see this type of drop, and then is that a particular issue for us in our reservoir simulation model? The last example, same thing. Here we go at 5,000 millidarcy feet at the half-foot log interval. Just over 5,000 millidarcy feet again in the Petrel world, up at 2 or 3 foot layer thickness, and by the time we come to eclipse, we're just over 4,500 millidarcy feet. So you can see at every upscaling step we are losing permeability thickness, but overall it doesn't seem to be too bad in this particular case. It wasn't particularly too much of a concern for us. And here I've tabulated the results of these 3 wells, and one of the nice things, of course, that it is good to do is be able to keep your reservoir engineer happy and match his well test results, and of course well test results can be open to some interpretation as well and ambiguity, but here we have those 3 wells. So we've got some calculated permeability thicknesses from these 3 wells: 3,500 millidarcy feet in well 1, 12,300 millidarcy feet in well 2, and 6,600 millidarcy feet in well 3. And through the process that I've just shown you in my log data set, I was in fact predicting 5,900 millidarcy feet, 13,000 millidarcy feet, and 5,000 millidarcy feet, which I tell you I've seen a lot worse than that, so that wasn't too bad. At the log scale, my predicted permeability using these flow condition permeability techniques is not a bad match to well tests, and it's always good, as I say, if you can agree with your reservoir engineer, it avoids some arguments. But of course we have to give our data over to the geologist, as I said, to interpret into his geological model. And as I've shown you that we lose a slight bit of permeability thickness in the 2D Petrel world, the upscale, so we're dropping down to 5,600 millidarcy feet here. Again, I'm repeating myself, I guess, again, because we're dropping down to 12,000 millidarcy feet, and we're dropping down to 5,000 millidarcy feet. But at the end of the day, by the time we give our reservoir model back to the reservoir engineers to simulate, we're sort of looking at a comparison between well test of 3,500 to 5,500, 12,300 to 10,300, 6,600 to 4,600. So that's a little bit different there, and indeed we're losing a bit of permeability in well 2. But anyway, we resolve these issues with our reservoir engineers. I'm just trying to illustrate here the sorts of comparisons that we can carry out and the sorts of discussions that you can then have with your reservoir engineer. And in fact, if you go back to the original Delfinia paper, there's a nice discussion there on how the upscaling techniques work and how sometimes it's appropriate to modify your original permeability equations through each upscaling step. And you can check as we go through the upscaling whether you need to do that. And there's quite a nice discussion there on the Delfinia paper about these kind of issues. Okay, so the final part of this presentation is focusing on net cutoffs, and I'm really just providing some food for thought here. I hope I'm trying to provide the case that are cutoffs relevant today. Obviously there's a tendency for us to let the simulator decide. In the olden days when petrophysicists were petrophysicists with their handheld calculators, their HP 41CVs and their slide rules, they would be the sole arbiters of net reservoir. So they would tell the reservoir engineer or the geologist the net to gross of this formation is X or Y, and the geologist would go away and map that up. But these days with 3D simulation models, that's not fashionable so much these days, and so petrophysicists are asked to characterize all of the rocks, be they what we would traditionally call non-net or net, and provide those results to the geologist to put in his simulation world or transfer into the simulation world. And then we would let the simulator decide actually what's physically able to flow in our models. So obviously there are some dangers with that approach, and some of the food for thought that I'm going to present here now is that hopefully will give you some ideas about what it is we talk about when we talk about this 1 millidarcy cutoff. What relevance does that have out in the real world? So what I'm trying to do is see if we can develop a feel for what's physically going on in the reservoir when we talk about this 1 millidarcy cutoff. And unfortunately, as I'm not really presenting any finite answers here, my objective is not really to muddy the waters, but just maybe get people thinking about cutoffs and how they change and are relevant for different production situations in their reservoirs with different fluid types, etc., etc. Okay, so here we are back with our routine 5K crossplot, and we've all done it in our time. We've taken what's typically taken as a 1 millidarcy cutoff permeability, and we transfer that down to see what porosity cutoff we should use in our net to gross determination in our G&G world. So it's quite typical, come in at 1 millidarcy, and in this particular example, first appearance, it would seem that we should be taking 9.5% porosity cutoff, and that would be a typical net to gross to take. But as we've shown already in this series, there's the brine correction to consider. I assume that this 1 millidarcy cutoff, if it's relevant to anything, should probably be relevant to an in-situ 1 millidarcy cutoff downhole in our reservoir, rather than a rather abstract concept of an air permeability in a laboratory. So if we take our 1 millidarcy in-situ liquid permeability, then in fact maybe I should be using an 11.6% porosity cutoff. And of course, as we've also mentioned, I mentioned in the previous presentation, there are degrees of overburden correction. Which in situ do we use? Do we use this one? I think this is a shaly sand, the UHAS shaly sand one, where all of the brine permeabilities are reduced from the air permeability, or should we go back to our simple case? Either way, there's some degree of ambiguity. Okay, so as a byproduct of my permeability methodologies here, I always calculate an expected flow rate for my given assumptions for my permeabilities. So here, using these wellbore fluid assumptions, I plot up here the permeability that we calculate and the expected flow rate in barrels of oil per day per foot. So let's consider this 1 millidarcy, this magical 1 millidarcy number. What does it mean in terms of real-world flow rates, if you like? As I say, in this particular example, if I come in here at 1 millidarcy, I see that in this particular reservoir I'm producing half a barrel of oil per day per foot. Doesn't seem too unreasonable. Now if I increase the viscosity of the wellbore, that's of the oil fluids, so I make it a much heavier, more viscous oil. Obviously I increase the viscosity, the flow rate drops. I lose about a tenth. I'm down to about a tenth of the flow rate because the viscosity is increased, and for that given drawdown, the flow rate drops. So what can I do to mitigate that? I could put in a jet pump, increase the flow rate, increase the drawdown certainly, and then I can get back to my half a barrel of oil a day with this higher viscosity if I increase the drawdown. So therefore that sort of hints at the impact of drawdown, so your cutoff may be production mechanism dependent. Okay, now if we go out into the reservoir further away from our wellbore, 2,000 foot out into the reservoir, we've got that 3,000 psi drawdown in the wellbore, but out here 2,000 foot away with exponential decline, we're only going to be seeing about 13 psi across our pore system. So we've got a 13 psi drawdown across our pore system with our thick viscous oil, and of course our flow rate drops quite considerably, 0.002 of a barrel per day. Now this 13 psi might look a bit low, but I guess it's important to recognize that our oilfield reservoirs typically can fill, and the buoyancy of the oil that drives oil into our reservoirs has to overcome capillary pressure effects to get into the pore space, and these sorts of forces are typically in the order of tens to low hundreds of psi. So this 13 psi is certainly well within the realms of force required to fill oil reservoirs. Admittedly, they fill over geological time, which may be a little bit more different, maybe a bit longer than we have in time to make profits in our production timescale, but nevertheless, in terms of orders of magnitude of force, if we can fill an oil reservoir with a force of tens of psi, then 13 psi drawdown is not an insignificant degree of force. Okay, so if we go back to our nice thin oil, our well-behaved thin oil, but keep the same drawdown, we're still out here at 2,000 feet away. We're flowing 0.02 of a barrel per day out here in the reservoir. If I drop the drawdown back in the wellbore, if I take that jet pump out and I reduce the drawdown at the wellbore to 300 psi again, remember our original case, that means that I've halved the pressure drop out here and the reservoir, and again my flow rate drops. So I'm only at 7 psi drawdown now, and I'm only flowing 0.01 of a barrel per foot. Now I guess with these low flow rates that also may be of concern, but if you think about the energy flux between the pressure flux between the wellbore and where we are 2,000 feet away, that's quite a large cross-sectional area. So although the flow rates themselves are very, very small, the flux is operating over a very large cross-sectional area, and so there's a fair bit of potential for fluid movement. And indeed, this is one of the things we like to let the reservoir simulator determine what's flowing for us and ultimately what's going to provide us with a commercial return. Okay, so if we need 0.1 barrel a foot per day, let's just make an arbitrary cutoff, say I'm only interested in oil if it flows at 0.1 barrel per foot per day. What should we be considering? So we've got 10 foot of rock could transmit a barrel of oil, and out here in the reservoir we'd need 9.5, nearly 10 millidarcies for the reservoir rock at this drawdown to be able to flow at this pseudo commercial limit. If we increase the drawdown back in the wellbore to 3,000 psi, again increasing the drawdown out here in the reservoir to 13 psi, then we drop the permeability we require. We only need 5 millidarcies, and we can flow this required 0.1 barrel per foot per day. Now let's go back to the wellbore. Let's get back at the wellbore itself. Under the same pressure conditions, 300 psi drawdown. If we need this 0.1 barrel per foot today to be commercial, then we only need 0.22 millidarcies to flow. So remember, out in the reservoir, that same flow rate, given that drawdown, we needed 5 millidarcies to flow. And here at the wellbore with this drawdown, we only need 0.22 millidarcies to flow. So hopefully this is giving you an insight to the fact that a 1 millidarcy cutoff, well, under what conditions are we considering that? Is that near wellbore, operating over a small cross-sectional area, if you like, or is it out in the reservoir where we are operating over a much larger cross-sectional area? So this universal application of a 1 millidarcy cutoff is fraught with danger and concern, and that's probably why we let the reservoir simulation model ultimately decide. Okay, so I've got one more example here. Say we just need 1 barrel of oil per foot per day. Somebody decides that at the wellbore in our reservoir pay in the wellbore we need 1 barrel of oil per foot per day to give us a commercial flow rate. Then we need 2.1 millidarcy feet in our reservoir at our wellbore. That would be our traditional pay cutoff. So not 1 millidarcy but 2.18 millidarcies. And of course we could go into our 5K crossplot with 2.18 millidarcy and we come out with a 12.6% porosity cutoff. Okay, so I've probably muddied the waters suitably there, but what I'm trying to get at here is that actually a 1 millidarcy cutoff, well, what does that mean? When we're picking cutoffs on well logs, you know, as a result of PLTs and seeing what's flowing into our well bores and trying to make a judgment of what's of interest to us today, we have to bear in mind that out in the reservoir over much larger cross-sectional areas, quite low flow rates and quite small pressure drawdowns can still ultimately deliver reserves to our well bores. As I say, I hope that kind of discussion at least gets you thinking along those sort of lines, rather than just saying, well, I'm using a 1 millidarcy cutoff. There's a little bit more to it than that. Okay, so finally, in conclusion, I would like to say that I hope that I've shown in the early part of this presentation that we can, by verifying the results of our upscaling processes with these graphical inflow profiles, we can get a good insight into any systematic bias that's creeping in, and also it gives us a good feel about what elements in our reservoir description are having the most impact and what are most significant to us, and that gives us a good view, a good insight for our reservoir modeling in general. Obviously this also gives us the opportunity to adjust our pore-perm relationships as we go through the upscaling process, and as I say, you can refer to that Delphina paper for a reasonable discussion on that. And matching to well test is key, so these are the sorts of issues that you can use this process to match to well test, and you can keep your reservoir engineers happy, keep them on board. And if you're not matching your well test, this graphical approach, looking at the inflow profile, can hopefully highlight where you're going wrong most, I guess. Okay, and the last part of my presentation that I tried to confuse you with, and myself, was the cutoff sensitivity considerations. They are complicated and dynamic, so ultimately, yes, of course, we have to leave it to the simulator. That's what it's there for. However, if we do investigate these issues in your particular reservoirs, with your particular rocks and fluids and your production mechanisms, pumps or drawdowns, then it can be very useful looking at things in that way, giving you an understanding of the key flow issues in your particular reservoir. Okay, thank you very much for your attention. Welcome to the second application presentation for my flow condition permeability modeling. In this presentation, I'd like to touch on some flow rate prediction work. Okay, you may recall this presentation slide before. This was in my second applications presentation. It's a cored well, it's a fairly tight sandstone reservoir, and this is the predicted flow profile. And in this particular well, we've got two fascies, an upper cloud of data points here and a lower cloud of data points here, and that corresponds to this upper sand package here and these lower sands down here. So those are the two fascies. We come up with two pore-perm trends for them, and we use those in an uncored well. So we're predicting permeability directly from porosity, hence the straight lines. Similar type of geology as the cored well, and under reservoir conditions, the water flow rate in this particular case over these perforated intervals is predicted to be around about 2,000 barrels of water per day. So what I'm interested in doing is actually calculating an expected injection profile. So with injection, we're actually injecting cold seawater, so the viscosity of the water is a lot higher, and in fact the pressures are a little bit higher as well, and so therefore the viscosity increases, and therefore the expected flow rate or injection cross flow rate, inflow rate is down to 600 barrels a day of water. So here we have the two straight lines, the two fascies, and so we would predict that we would be able to inject 600 barrels of water per day. Now, one of the things that I was considering is that, okay, you may remember that core data. Obviously, whenever we make a prediction of permeability from porosity, there's obviously a scatter of the real core data around the place, and now here in this instance we've obviously got a straight line relationship, and that scatter is gone. So if we put it back, if we put some simulated core noise, I know how good my core pore perm fit was, so I know the standard deviation of the error around that fit. If I add in some statistical noise to simulate that core fit error, I do the same with both of the fascies. Now this is still log data, but I've put in some simulated noise. If I flick back to the real core, keep in mind that sort of data spread there. If I look at the cored well, it's a different well of course, and in our new well I've got a little bit higher porosity, but as you can see that sort of spread, what I'm trying to do here is simulate that kind of spread, and in this particular case I've got a bit more higher porosity data up in this particular fascies. But what I'm doing is I'm adding simulated core fit noise with both fascies, and you can see that in this particular case I'm up at 935 barrels of water per day. So with simulated noise I seem to get some more injection away. Now is that real? Or let's have a look. So what we can do is we can do it a number of times. That's the nice thing about simulated noise. We can press the F9 button and recalculate our random numbers and add in different type of noise. So here I've got 1100 barrels a day. I can do this twice, 3 times, and each time you see all I'm doing is I'm varying the error. I'm taking the same statistical error on my core pore perm fit, and I'm adding in a random bit of noise, and you can see that I get a variation in flow profile. Okay, so this noise is just driven by the spread of error in my original core pore perm prediction, and I'm getting a range of injection rates. So in fact I can carry on doing that, and rather than me click through it laboriously like that, I can continue with a full Monte Carlo simulation with this random noise. Okay, so here we go, some Monte Carlo simulation, whole range of them. Let's run 10,000 of them. So we keep the average porosity constant in this case. This is a logged well. We have a measurement of porosity. We're just looking now at the error introduced by the residual fit, and at the end of that process we can capture some statistics about the simulation run. We can work out some distributions, and at the end of the day we can go forward after that simulation and predict after 10,000 trials what our most likely injection rate would be. And we find that the P50, the most likely, or sort of the median case, is 1100 barrels a day. And you can see it's a little bit negatively skewed, so it's more likely we're going to get the lower numbers than we are the higher numbers. Okay, so that's pretty clear then. One thing to note, as I said, the standard deviation of the porosity we've used is quite small. That's because this is a logged well. We know what the porosity is, so the error in permeability we're predicting is the error due to that original pore perm transform error. Now, however, what if we don't have a logged well? What if we're looking at a new well where we don't know what the porosity is? Then we can put in a pseudo porosity, but this time we don't know what the porosity is really. So the porosity of each individual unit can be allowed to vary too. So if you like, we need to model a situation where we put in this geological noise. Now, I think if you go to my residual oil presentation, there's some discussion about error analysis in there. And if you look at the porosity in a logged well, of course, there are errors in the calculated porosity. We don't know everything, of course. We make some assumptions down the wellbore about the effective fluid in the formation, the matrix density. There will be, of course, tool errors and precision inconsistencies down the well. But on the whole, providing the tool is calibrated correctly and we don't have any systematic shift because of that, the error in porosity will be, plus or minus 1 pu, say, and that's the tool, that's the error in the calculated porosity. So we add in the error in porosity, 1 plus or minus 1 pu, and the error in our poroperm prediction, and that was what was giving us our random error in that last well. In the case of an unlogged well, of course, we don't really know what the porosity is going to be, but we know how the porosity could vary geologically, between wells. We know what the range of geological variation is. So if we allow the porosity to vary by layer, and let's just take the upper package and the lower package, and we add in this simulated geological error, if you like, so that's more of a systematic error. So in addition to our poroperm error, our prediction poroperm error, we add in this geological noise, this systematic noise, and again we can run a number of trials. And here you may see that the actual porosity of the layer can vary as well. So we're not keeping the overall average porosity the same. We're allowing the porosity in each geological layer to vary by some amount. Okay, so we've got a range of realizations here. And again, we can once again continue with our full Monte Carlo simulation, looking at systematic errors. And here you'll see that the porosity of each layer is varying independently. And once again, we can run the simulation and get an idea of our expected flow rates. And at the end of that process, we can collect the same amount of statistics. Here they come now, and a whole bunch of stuff that we learn about that simulation run, and we use that to predict what our expected flow rate is. So with this additional geological noise, we find that our mean expected flow rate is 762 barrels of water per day, and you can see it's a much more negatively skewed log normal distribution. So there's a chance that we'll get some high rates away, but on the whole, things are looking a little bit poorer. Okay, and here if we look at the standard deviation of the porosity through those simulations, I've allowed it to vary, and this is the sort of range we see in the well data. And in fact, in this particular field, that's it. The wells are pretty consistent. The sand is very well sorted, and there isn't much variation in it. But nevertheless, the principle is clear that there's a geological noise in uncored wells. When you're making a prediction about how a future well will perform, you need to add in that geological or systematic noise, as well as your random noise from your error prediction. So, the conclusions for this particular study were that we expected we'd get around about 760 barrels of water per day away. There was a 10% chance that we could get up to 2,400 barrels of water per day away, but we were 90% sure that at least we should be able to get a minimum of 250 barrels of water per day away. Now, these numbers are pretty low by North Sea standards, but in this particular low deliverability, low permeability reservoir, these sorts of numbers are unfortunately about par for the course. So I hope I've been able to show that we've been able to use the degree of error in our original poroperm transform to actually be able to calculate a realistic range of expected performance. And obviously out in the real world it's often quite handy to be able to deal with ranges of expected outcomes. We can put ranges into our economic evaluations, and rather than be reliant on one particular realization, we go in with one porosity and come out with one permeability. There are uncertainties associated with that, as we've said, and if we can get a better handle on a realistic range of expected outcomes, then that hopefully means that we can make better decisions. I should point out, of course, that this particular example is an injection well, where when we're injecting cold water into reservoirs, we often get localized induced fracturing and other such localized features enhancements due to the injection process. So therefore it may not particularly be indicative of the original matrix performance, and hence obviously our poorer perm prediction is originally based on the expected matrix performance from our core data. So obviously you need to take into account the effects of the injection process, but the main purpose of this particular presentation was really to illustrate the fact that when we add realistic noise back into our poorer perm transforms, hopefully we can make a better estimate of realistic ranges of expected performance. Okay, well, thank you very much. I hope you found that interesting or useful. Thank you very much for your attention.